Okay, so Chenjun has been here for a while. So he was a master student with me working on games stuff. And recently he's been working on a large number of different topics in RL. And yeah, so this is his most recent RL paper from ICML, and he's going to tell us why it's in general a bad idea to use online algorithms for the batch case. At least that's how I understood what he's doing. So without further ado, Chenjun, please.
Okay, sure. Can you guys hear me? Good.
Yes.
Okay, so yeah, thanks for coming to my talk. So today I'm gonna talk about what's the optimal algorithm in batch reinforcement learning. And this is a joint work with Yifan and Tor, Bo, Jincheng, Li Hong, Chaba, and Dale. So the problem we want to look at is batch RL, or the so-called offline RL setting. And this is like some picture I got from the website. We show the difference between like online RL and offline RL. So in online RL, your learner can interact with the environment, collect the data, and using that data to adapt your policy to further collect more data and learning best sequential decision-making policy from that procedure. But in offline RL, so we have like logged in, like some fake logged data set which have like several interactions from the environment before, and your algorithm only want to take that data set as input and output and good action. So the difference is that in the offline setting, your data set is fixed. You cannot do any further additional interactions, collecting more data. And you can see like this has many applications because we have like tremendous amount of data for many applications, and we want to grab some very good sequential decision making policy for that application. And so the problem we want to like answer in this paper is like, what's the optimal algorithm in this problem setting? And the motivation is that we all know optimism is in the online setting is simultaneously both like minimax optimal and instance dependent optimal. So this makes that the OFU principle, or like optimism in front of uncertainty, is the intrinsically best principle for decision making this exploration problem. So we are wondering if we have same algorithm has the same property in the batch setting. And so that's our motivation of the paper. And we especially want to know if pessimism have such property, because as you may know, like in recent years, there are many papers coming out try to suggesting pessimistic is a really good idea in this batch reinforcement learning problem. And we just want to know if that's true. So that's the motivation. And to study this problem, we consider a very simple clean setting, which is Bandit setting. And but it's kind of different where like your data is fixed, so we call it offline Bandit. And as you can see, there's still like arms in this problem. And for each arm, we have like an unknown reward distribution PI. And for that arm, we have an ID sample from this distribution PI. That gives you like empirical observation of that arm. So this consists the whole data set. Like for each arm, you have NI different observation. And your algorithm just want to take that data set and as input and output action. And the objective is try to minimize the so-called simple regret, which is like you compare your algorithm's choice with the best possible payoff you can get in this problem. And of course, we define like a problem instance is defined by a difference of the counts of observation for each arm, and also the unknown payoff reward distribution. And So the way we try to look at into this problem is we want to consider the so-called index algorithm. And the index algorithm has two, so like basically it first compute the index for each arm and then select action according to the best index. So the mu hat here is the empirical mean, like you just basically like get the NI observation for each arm and compute this empirical estimation for the reward. And also an extra term based on the number of count for that arm. So this kind of tells you how much confidence you have, you know about that term. If NI is very large, you are very, very confident about that. And if NI is very small, you are not very confident. And alpha is like a free parameter chosen by your algorithm. So your algorithm can define the alpha, then put into this index that defines the algorithm. So, and actually we can define this using this, choose this alpha in a specific way. So the idea is that, so by Hofstein's inequality, we know if you're using this confidence like beta delta, so delta is like some small probability. If you define your index using this beta, we know your true reward will is in this range with high probability for that term. So like different alpha can recover all kinds of algorithms. For example, if you're choosing your alpha using this minus beta delta, you get the LCB algorithm. And if you're choosing alpha with like positive beta delta, you get the UCB. And if you're choosing alpha equal to 0, you get the so-called greedy algorithm, which just pick action based on the empirical mean. So the reason we want to define this index algorithm is because this provides this unified view to analyze the whole family of algorithms at the same time. Okay. So, and you may want to know like why, like what's the intuition behind the pessimistic? So this is like a picture from a recent paper suggesting pessimistic is probably efficient in your scenario. And this is also like a simple illustration in a Bandit problem. So here you can see we have like 8 arms, and so the arm 1 is a very good choice, and the last arm is a very bad choice. And because you have in your data set, you only have a very few observations for that action. So it can give you a very high empirical estimation for the arm because the variance can be high when you have a very small number of samples. So then there's a problem if you want to select the action according to the empirical mean. And like according to this picture, the algorithm selects the best empirical mean. You will just pick the worst arm in this case. So the idea is just, so the ideal pessimistic will be, we want to get some conservative estimation for each arm and selecting according to that conservative estimation. And actually, like there are some favorable bound for the idea of the LCD or the pessimistic algorithm. So so you consider the pessimistic algorithm which choosing the action with the highest LCD, and we're using this I prime as the output of the pessimistic algorithm. So you can get this upper bound for the simple regret. So we assume like all the high probability event holds, like the true reward is actually inside the LCD and UCB in that range. So we first get so we want to compare the payoff of I prime with the optimal payoff mu star. So the first inequality comes from the fact that LCB is a lower bound for the true reward. And then the second inequality follows by you choosing the LCB by picking the highest LCB action. And then you get that the regrets of the pessimistic algorithm is decided by the confidence interval of the best action. So that's kind of like, so it's kind of suggesting that if your good action has been pulled many times in your data set, then the LCB will have very small simple regret. But is this actually good enough? So actually, we can derive a very similar property for any index algorithms. So if you define the mu tilde as the index of R, so we can do the following composition. So we plug in the index for the A star and plug in the index for the I prime. So I prime is your algorithm output, which is arm with the highest index. And the first inequality is followed by your definition of your algorithm. So this is real smaller than 0. And then, of course, your index is decided by your confidence interval. So the difference between your index and the true reward mean it has to be controlled by the how large the confidence interval of that term. So in summary, this will give you the upper bound of a simple regret of any confidence index algorithm according to this, the worst case, the largest possible confidence interval. So, and you may notice that the LCB only depends on the optimal action, and for general index algorithm, it depends on the worst, the action with the minimum number of poles. But in the worst case, it doesn't really matter because data set A star can be pulled very, very small number of times. So so this comes to our first contribution. So theorem 1 gives you the minimax lower bound for this problem. So basically, for each action, you can find a very bad problem instance for that algorithm. And then this is a definition of the minimax regret. It controlled by so you can see the right hand side is lower bounded by the lower, largest possible confidence interval. So that's in the worst case, how much your algorithm can suffer in this problem. And theorem 2 shows that for any confidence-based index algorithms, the simple regret is upper bounded by the largest confidence interval. So if you ignore the log factor here, you can see any confidence index algorithm nearly minimax optimal. And this just tell you minimax optimal is too weak to distinguish all these algorithms in this offline RL problem and offline Bandit problem. And so any question for now? Okay, so I'll move on. So now then we move to the instance dependent analysis, and because the minimax optimal is just too weak to distinguish all these algorithms. So this is the next picture from the Bandit algorithms by Tora and Chaba. So we're showing the showing the basic idea of the instance dependent lower bound. So in the axis, it's the instance, and the y-axis is of course the regret. So so this horizontal line is the minimax optimal, because that the minimax optimal is the worst case regret you can get for this problem. So it's the same for all the instances. It doesn't depend on the instance actually. And this line is the instance dependent optimal at lower bound. So because in some problems, things could be very easier, but some problems could be hard. So your regret can change. The regret lower bound can change for different instances. And this is a regret for a particular algorithm. So you can see this algorithm only can be very efficient for a particular some instance. For example, your algorithm can simply pull one action all the time, and of course you can find some instance that the simple regret of the algorithm is very good. So this is the idea of the instance dependent lower bound. So basically, you want to get a measure how hard the problem is for each problem instance, and we want to only compare the algorithm according to that measure of hardness. And so we So now we like consider this instance-dependent analysis. So we first define a set of minimax optimal algorithms. So so the set of minimax algorithms defined by this constant C, and also we fix the number of counts, like we fix the number of observations for the arms. So defined by this constant C, the minimax, the set of minimax optimal algorithm it cannot be, so the regret upper bound for any instance is upper bounded by some constant some constant times the minimax optimality, the regret. That means like up to constant C, your algorithm is minimax optimal. So that's a set of minimax optimal algorithms. Then the instance dependent lower bound is just within this minimax optimal algorithms. So if I give you an instance theta, then I want to find the best minimax optimal algorithm from that set and measure the regret of that algorithm on that particular problem theta. So that's the definition of this instance dependent lower bound. And so now it comes to like the punchline of our paper. So this result suggests that no algorithm can be instance dependent optimal in this problem. So the way you can interpret this result is, so for each problem instance theta, we compare algorithm with the best minimax algorithm on that problem instance theta. And if you take the maximum of that, and the ratio can be arbitrarily large. So this tells you for any theta, I can always find some algorithm to make the algorithm like arbitrarily better than the best algorithm on that theta. And so this is like so this will become like totally different with the online setting, because in online setting we get the optimistic algorithm is both minimax optimal and instance dependent optimal, but in this problem there's no instance dependent optimal algorithm. And yeah, so any question here? Okay, so I'll move on. So this is like the simple two-arm example suggesting the idea behind this instance-dependent lower bound. So and if you consider like the simple two-arm case, and for N1 we have like lots of observation for that action, and that basically means we almost know the true reward of that action. And for arm2, we don't have like enough evidence for that action. So then, So then like it's really hard to, from this problem, it's really hard to know whether LCB or UCB is good. Because if mu1 really is smaller than mu2, then UCB will win, because like the exploration will let you choosing this optimal arm too. But if mu1 is really bigger than mu2, so then LCB win, because you like the mu2 have very small number of exploration, which give you overestimate of the action, which led you actually choosing the bad arm. And we actually run some simple two-arm simulation for this problem and compare the regret of all different algorithms. So in this example, we fix the number of poles for N1 and N2 and only change the reward gap between N1 and mu1 and mu2. So axis is the mu1 minus mu2. So from the left go to the right, mu1 becomes the like from the bad choice go to the good choice. But the count is fixed and the reward distribution is Gaussian. So you can see that actually the performance of LCB and UCB are almost symmetric here. And the reason you can see a curve like looks like this is because if the reward gap is very large, then the problem is simple. And if the reward gap is really small, the problem is also simple. So you will see the curve looks like this. But the idea is that from this two-arm case, it's clearly that UCB and LCB is equally bad in some sense, equally good or equally bad in some sense. And you cannot really say one algorithm dominated the others. And that's kind of counterintuitive because we all believe UCB is a bad choice for this batch problem, but actually it's not, especially when you consider this two-arm case. And so then we do some like upper bound, instance-dependent upper bound analysis for the problem. So for LCB, we like for all these LCB, greedy UCB, we derive the instance-dependent upper bound. And for LCB, you can see that so here we are, sorry, for the easier presentation, we assume like mu1 bigger than mu2 bigger than μk. So like mu1 is the best arm, and the delta is the reward gap of that of arm I with respect to the optimal arm. So you can see in the regret upper bound of LCB, so if a very good action has been pulled many, many times, then this quantity will be small. Then your LCB will has very small simple regret. And for the UCB, it's actually very hard to make that candidate. So for UCB, it's like have some. So I need to, all my bad actions has to be pulled many, many times to make this algorithm performs very well. And for the greedy algorithm case, kind of in the middle. So although like we cannot say like one algorithm is instance-dependent optimal according to our previous results, but from this regret upper bound, you can kind of see some property of the algorithms. So to verify this, we also run some simulations. And so in these two data sets, so in the two data sets in the above two figures, the behavior policy to collecting the data is like the epsilon greedy one. So so there's like 100 arms. We sample each arm according to the epsilon greedy one, greedy policy. And that means like the good action has been pulled many, many times. And you can see LCB is much better than the other two algorithms. But in the below the two figures, the behavioral policy try to sample the bad arms very, very often, much often. Then you can see UCB dominates the other two algorithms. And that's kind of verify the property of each algorithm. And finally, because like as we shown before, you cannot like almost any confidence index algorithms are minimax optimal, and there is no instance dependent optimal algorithms. So far we don't have any definition that can really tells you like which algorithm is the optimal choice. So then actually we can define some weighted minimax and use that as argument to favor one particular algorithms. So the idea actually go back to the instance dependent optimal definition. So if you go back here, and as I suggested before, this quantity is kind of like the measurement of how hard that problem theta is. And you want to measure the performance of algorithm under that hardness measure. And if you're choosing this like most obvious way, like how the best optimal, like minimax optimal algorithm can perform on that instance, we can also like such instance dependent optimal algorithm exists. So the idea is just we want to change this hardness measure from that for that instance, and that comes to this definition, which is like how hard this problem is if you want to measure the true, like the true reward of the optimal value. So this new n theta is a set of minimax estimator for this problem, I want to using the best algorithm, the measurement of the best, like the error of the best estimator for that problem as a hardness measure for that theta. Then we weight each instance using that weighting, then show LCB is nearly optimal under this weighted minimax setting. And under the same ratio, you can show like UCB and greedy have infinite upper bound on this ratio. So it's kind of, so actually the weighting can be defined in, so it's just one way to characterize when LCB is optimal. But actually you can define many different weighting to favor different algorithms, because like our previous result basically tells you all the confidence index algorithms are at the Pareto frontier of the problem. So you can define certain way to favor one particular algorithms. And so what I want to say is just that this is just kind of some intuition to verify when LCB is the best algorithms. And so this comes to the conclusion of our paper. So we first show that any confidence index algorithm is nearly minimax optimal. So you cannot really use minimax optimal to distinguish all these algorithms. And then we show like no algorithm can be instance dependent optimal in this batch of like batch reinforcement learning problem. Like, sorry, like what I want to remark is that although our result is for the Bandit setting, but because it's a lower bound. So if you want to move to the harder setting like linear Bandit or reinforcement learning, this lower bound still holds. So you cannot find any instance dependent algorithms. And finally, we show that pessimistic algorithm can be justified using some weighted minimax optimal definition. And yeah, I think that's everything. Thanks.
Does anyone have any questions?
Yeah, can you walk me through, oh, sorry, I see Roshan's got his hand raised.
Yeah.
Sorry, go ahead, I'll go after you.
Sure, thanks. So can you go back to the weighted minimax results? And I'm just trying to make sure I understand exactly what this means. Like, you were saying when you can justify using your pessimistic algorithms. So can you sort of characterize or give me some intuition for what this result says to a practitioner? Like, what would a practitioner need to know about his problem in order to think I should use a pessimistic algorithm?
Yeah, so the intuition is kind of similar as suggested by the upper bound. So in the upper bound, we know like if your data set has been, like if your behavioral policy to sample a data set is like epsilon greedy, for example, it's based on the optimal like, policy, then LCB performs very well. And this weighting actually closely related to that quantity. So if your optimal arm has been observed many times, then this estimation problem will be much easier. So it's kind of like the intuition is that if your optimal arm has been poor many times, LCB will be better. And we find some problem that related to that property.
Mm-hmm. So sort of ironically, if you were optimistic about how your batch data set was collected, then pessimism is a good way to deal with it.
Yeah, so that's actually we found in many practical papers. If you look at all these offline RL data set like D4 RL or other data sets, you can find that if you want to make your algorithm perform very well, that's almost only happen when your data set is collected by a good policy.
Mm-hmm.
So yeah, that's what we found in all these empirical papers also.
Mhm.
And I think our paper like tells you why that happens.
Yeah. Okay. Thank you.
Any other questions?
Yeah, sorry, can you hear me?
Yeah.
Yeah, you're good.
Yeah, so I had a similar question, and I was also wondering about the meaning of this weighted minimax. And I was just
Mhm.
thinking if you had any ideas about like other similar metrics. So I guess one thing that weighted minimax is doing is it's just doing this weighting by the inherent difficulty of that instance, right? But what if you
Yeah,
had something else where you said something like, I will create a class of instances that is known to be easy, right? Where this might be small, and I want to do the best in that class. So something more like splitting up the class of instances based. Like, do you have any thoughts on how that differs, or whether it's the same?
Yeah, so actually, if you look at those pessimistic papers, let's theoretical results for pessimistic, so they're also using some kind of weighting. For example, in the paper called "Is Pessimistic Probably Efficient in FlyRL?" what they use is like kind of like the variance of your data set under the optimal policy. So that's kind of tells you your weighting is if your optimal policy has been covered by the data set, then the problem is easier. If your data set cannot cover the optimal action, like optimal policy enough, then the problem is harder. So this is kind of similar as this quantity because they all related to like really how your data set is collected, if it's collected by the optimal policy or not. So yeah, actually you can define many different weighting, I think, in principle to favor one particular algorithm, because that's basically our instance-dependent lower bound suggested.
And maybe this is sort of looking at it from the other direction, but is there any weighting that you can think of that makes optimistic algorithms, like what kind of weighting would make optimistic algorithms good algorithms?
Yeah, so for example, in this two-arm case, your weighting will be like the weighting you want to design will be if the bad action has to be pulled many times, then this is true.
Okay, so if the bad action is represented in your data, then you want to be optimistic. But if the good action is represented, then you want to be pessimistic. Okay.
Yeah. So like if the K-arm case will be harder, right? Because you want to all the bad action has been pulled enough. But in this two-arm case, it's very symmetric, right? So
it helps a lot. Yeah. Thank you.
That's kind of yeah.
Are there any other questions for Chenjun? Okay, if there's no more questions, I guess we can end a little bit early today and give everybody back 20 minutes of their lunchtime. So thank you very much, Chenjun, for presenting. And if anyone thinks of any questions after the fact, feel free to reach out to him or reach out to me if you don't have his email address, and we can connect you. So thanks again for coming to the presentation, everyone. And have a wonderful weekend.